Hello everyone. In this lecture, we will have a look at insertion and search operations and how they are implemented in binary search tree. As we remember from the previous lecture, binary search tree has four common operations as insert data for insertion of data element, search data, searching a data element, delete data, deleting a data element, and tree traversing algorithms for traversing through the binary search tree. We will see deletion and traversals in the next lectures, but for now, let's continue with insert and search operations. To understand how the operations work in binary search tree, we first need to have a binary search tree. Initialization of a binary search tree can be achieved by simply doing the following implementation. As we know from methodology, every binary search tree should start with a root node, and a root node should contain left and right subtree. To create left and right subtree, we need to declare two nodes which will point to corresponding sides as left and right. As you see from this example, we have separate class of tree node. We use tree node class as a separate class to be able to initialize our binary search tree to a desired state when needed for further operations. Every node comes with a data or set of data. Data can be any type of data. But we shouldn't forget that to form a binary search tree, we need to extract a unique key for every node. Extraction of key can be achieved in a couple of ways. One way could be by creating a method or couple of methods that will return a unique key to be used for a node. In our example, we will simply use integer type of data and use same data as our key value. To see how insertion operation works in binary search tree, we will have our recursion listed in method call. This way, we can follow and have better understanding on how insertion works in binary search tree. So let's go on and insert number 10 in our binary search tree. To insert data to an empty or non-empty binary search tree, we need to start from root and do required actions towards the other nodes to dedicate the location of the newly created inserted node in our binary search tree. Therefore, we have an insert method with two input arguments, one for root and one for data to be inserted. So, 10 is our first data element to be inserted in our binary search tree. We check if our binary search tree is empty. It is empty. So, we set our first data into root node and return our root node. As we do not have any method call, we finish with our current insert. Next, let's insert data element of 13 in our binary search tree. We know that tree node's root is 10 and data to be inserted is 13. We also know that our binary search tree is no longer empty, so we skip the first if statement. And now check if the data is smaller than root's data. 13 is bigger than 10, so we skip to the next if statement. At the second check, we know that 13 is bigger than 10. So we point our new root as the right of the actual root and apply our recursion. To keep track of our recursive state, we can write line number where we left our previous run and current state at that line. We left at line number 9, where root is 10 and data element is 13. Now, our insert method will take new arguments as root.write and the data element of 13. Here, pay attention that our root.write is actually null, so the system will execute if statement and set our new root with the data element of 13. We return from this call method and go to previous method call. We know that we have left previous method call at line number 9 where root was 10. Returning root will be returning our root node to 10. As we have set our root.write to 13 at previous call, we will now have root with the data element of 10 and root.write as 13. Inserting lower data element than 10 would basically do same operation with only one difference. Instead of root.write, it would do it for root.left. Insert operation binary search tree has linear time complexity of big O(n) in worst case. But however, we should highly consider that its worst case occurrence probability is significantly lower than many known abstract data types. big O and linear time complex, the occurrence with insert operation binary search tree would only be possible if binary search tree has formed only at one side rather than at right or at left. This said, let's go on and see the search operation in binary search tree. Search operation is used to search a data element in binary search tree and return its value. So from already formed binary search tree, let's go on and search a data element of 3. So not much difference here. It is same just like in the previous method. We have two search methods. The first search method is to input data element to be searched, and the second is to pass the root node where we start searching from. To keep track of execution, let's create method call and go step by step to see our search method in action. At first if statement, we basically check if our binary search tree is empty. An empty binary search tree wouldn't store a data element, so we don't take unnecessary actions, but we return from function immediately. As our root is not null, we go next and check if our data is smaller than the root's data. This would let system to focus at only one side in binary search tree. In our case, 3 is smaller than 10. So we use recursion here and set our new root as root.left and the data element of 3. As we will have another method call, let's keep the information about the current method call. We are leaving this method call at line number 7, where root is 10 and data element or value is 3. We know that our root is now 7. It is not empty and not equal to data element of 3, so we skip to second if condition check. At the second if statement, we check if data is smaller than the root's data. As 3 is smaller than 10, if statement will be executed and we will be having another recursive call. Again, our new root is now current root's left node, which is 3. So at the next method call, our root is now 3 and the value is 3. At the first if statement, we check if root is equal to null or root's data is equal to data element that we are looking for. It is not null, but it is equal to data element that we are looking for. So we return the root, which is 3. As we return from our current method call, system will go to previous method call. At the previous method call, we have left at line number 7. As if statement was true at this line and we have executed it, system will skip the else statement and get the previous method call with assigned values. At this method call, we have left at line number 7. So same as the previous method call, we skip the else statement with assigned values where root is 10. So similar actions would be taken if the search data element would be bigger than the root. But this time, instead of root's left, we would look at the root's right node and search the data element at that subtree. As in insert method, search operation in binary search tree has linear time complexity of O(n). And again, just like in insert operation, big O(n) linear time complexity occurrence with search operation in binary search tree would only be possible if binary search tree has formed linearly at one side, rather only at right or at left. So in this lecture, we have learned about search and insert operations. In the next lecture, we will look at delete operation and implement it in binary search tree. So thank you for your attention. See you until next time in the next lecture.